Hi, my name is Emma Hayden, and this is my presentation for Physics 2211 Lab 4, Oscillations. In this lab, I studied an oscillating spring mass system to see whether energy is conserved during its motion. I'll walk through what I did, how I modeled it, and what I found. The goal of this lab was to analyze and model the motion of a spring mass system. With a pre-recorded video of a hanging mass bouncing on a spring, I used Tracker to collect its position data in both the X and Y directions. Then I used a code that was given and I edited it to simulate the motion using the forces of gravity and the spring. I compared my simulated graphs to the Tracker data to see how well my model matched reality. The main question was whether the total change in energy would equal zero, meaning energy was conserved. From my results, I found that the total energy remained nearly constant, confirming the energy principle. So these are some fundamental principles I used for this lab. The key concept behind this lab is energy conservation. If no external work is done, the total change in energy should be zero, meaning energy only changes forms within the system. I also used Newton's second law, the gravitational force, position update formula, the spring force, and velocity update formula to help me. Some key takeaways/assumptions was, if we assume no external work is done on the system by its surroundings, the total change in energy should be zero. In practice, though, it's nearly impossible to account for every factor that can do work on the system, so there will likely be a small non-zero change in energy. Some assumptions are, 1. Heat transfer is ignored, so the energy of the system remains, the change in energy of the system is zero. And then 2. Only gravity and the spring force are considered. And 3. Motion is limited to 2 dimensions, so the z direction is ignored, we're just dealing with x and y. So in Tracker, I put my initial conditions. I found the mass was 0.402 kilograms. The position was negative 0.116, negative 0.640, 0 meters. The initial velocity was 0 meters per second, and the length, L, was 0.7 meters. And then some parameters was the spring constant, of course, and then the reference length, which was 0.123 meters. So in the code, I initialized all the physical parameters. So in that case, the mass, the position, and then the velocity. So I tracked how energy shifted among the three forms, spring potential and gravitational potential. And then when the mass was lowest, spring energy was highest, and gravitational energy was lowest. And then when it was the highest, the opposite had occurred. For the coding loop, my simulation used a time-step loop that repeatedly calculated the net force, which was spring plus gravity. And then it used the update velocity and position over tiny time intervals. So running this over, the experiment's duration produced simulated position data, and I could compare directly with the Tracker data. This showed how closely my computational model matched the actual motion. So the total energy of the system stayed roughly constant, meaning the change in energy was equal to zero, consistent with the energy principle. So some deviations, though, were the tracking error. So slight inaccuracies in marking the mass or calibrating the scale and Tracker. It's possible air resistance, like real air drag, wasn't modeled, which could slightly reduce total mechanical energy. And then human error, so small mismeasurements or timing offsets. But despite these, my data strongly supported that energy was conserved overall. So was the energy principle satisfied? The results confirm that the energy principle is satisfied. Although energy continuously changes forms within the system, the total change in energy remains zero. This indicates that no net external forces are acting on the system, and therefore energy is conserved throughout the motion. I measured the oscillation periods in both directions, horizontal, which was x, about 1.677 seconds, and then the vertical y, about 1.519 seconds. They're close but not identical. The small difference likely comes from air resistance or slight tracking inaccuracy, which can affect horizontal motion more. Overall, both showed consistent periodic behavior. In summary, I successfully analyzed a two-dimensional spring mass oscillation using both experiment and simulation. The mass moved in both x and y directions, and my results showed that the total energy remained constant as it shifted between kinetic, gravitational, and spring potential forms. The Tracker data and code agreed closely, confirming that the system conserved energy. The small differences between horizontal and vertical periods were likely due to minor experimental effects. Overall, this lab demonstrated how well fundamental physics principles, especially energy conservation, can predict real complex motion. Thank you.